This is lecture 31. We are discussing the issues surrounding external fragmentation and the use of indirection to address the problem. So external fragmentation, which is a phenomenon that is quite serious, and the solution approach is through what we term in computer science indirection. So I'll give another example to make sure that this technique is understood. So suppose that we have here, so here's our actual physical main memory. So this is our physical memory. So here it is. And suppose that there is a process that's running, and the process, say P5, is, and I'm just making it Xeno specific, but this applies to Linux, Windows, Unix, to all operating systems. So in Xeno, suppose that a process P5 is running and it makes a system call and it requests getMem, say of 200 megabytes of memory. And I'm going to keep these things loose so that the concepts are clear. Of course, you have to all translate this into exact numbers. But so a process asks for 200 megabytes of memory from heap. Suppose that in this physical memory, there are two areas of free memory still left. So that would be the free list, and that area here is this piece of size 100 megabytes, and this piece down here also of size 100 megabytes. But that's it. There's no memory here that is contiguous and at least 200 megabytes. The largest one are these two pieces. Together, of course, they would suffice, since together they are 200 megabytes, and so together they would satisfy this request, but there's no individual region which would meet this request. And so in the absence of such a solution, this system call would return an error saying, I don't have this much memory, because it doesn't have contiguous memory left. That's this much. It has total memory, so the total is enough, but total is not the same as contiguous memory. So we have to always distinguish between total and contiguous. But the idea is not to give up. So the trick of indirection is we are going to create an illusion through indirection where the user thinks this is the user's memory. So this is the actual physical memory. There's only one physical memory, but the process P5 thinks that this is its physical memory. So it's illusory, so it's fake, it's virtual. And suppose that we are going to return from getMem with success. So not an error, but we are going to return from getMem with success, giving back a pointer. So it's not going to be an error, but it's going to be successful. And what we are going to do is, suppose we are going to return this address from here till here of size 200 megabytes. And suppose that this beginning address here is, let's say, 2 billion. Yeah, 2 billion with a capital B. So getMem is going to return, so this is the address, 2 billion, saying, hey, yes, I'm giving you 200 megabytes of contiguous memory starting at address 2 billion. So therefore the ending address would be, the ending address here is 2.2 billion. Of course, it is one less than that since we are starting at 2 billion, but let's not worry about these minor details. The key thing is that you get the concept, and then you need to make sure that all the numbers, of course, fit. So the ending address is 2.2 since we're getting 200 megabytes, which is 0.2 billion, and then 2 billion. Of course, this all happens in this abstracted notion of memory, which is not the actual physical memory. This is how the physical memory actually looks like. But getmem will now succeed and give back 2 billion. So how does the system using indirection manage to do that? The way that the system manages to do that is half of this memory, this fake memory, this virtual memory, is going to be mapped through indirection to this region, because this is 100 obviously, and this is 100, so this is half, and this is 100 that's actually free in physical memory, same here. So this gets mapped to here, and this piece here, let me show in dotted line, gets mapped to here. What does it mean to get mapped here? Suppose this address here, so this actual physical address of this contiguous 100 megabyte area in the true physical memory, suppose this address is 1 billion. Therefore, the ending address, because it's of size 100 megabytes, would be 1.1 billion. Just an example. Suppose this beginning address of this contiguous area of 100 megabyte size in the true physical memory, suppose it's located at 3 billion. That's the address. So hence, the ending address by this region would be 3.1 billion. So it's obviously a setup from this example. And suppose this process, after it gets back from getmem, what does it get back? It gets back the address 2 billion. That's the pointer. The address 2 billion, because it thinks it's contiguous and it starts at 2 billion, and because it's 200 megabytes, it ends at 2.2 billion in this fake address. The actual true location, the true addresses are this guy until here, which would be, so the middle point here is obviously 2.1 billion. That's the address. So this guy of course minus 1, because we are counting from 2 billion, gets mapped to here, and this guy gets mapped to here. And suppose after it does getmem and it gets back this address, it accesses the memory and it populates this area with all zeros. So suppose it puts all zeros here. So every address in this range has content 0 being placed. And suppose in this 100 megabytes it sets, so in some code here, it sets this content to be all ones. 1, 1, 1, everywhere it's ones. But of course, there is no such thing. This is purely an illusory memory. This content lives where it must live in the actual physical memory. So therefore, from here till this half point mark, where are they actually located? At this addresses from 1 billion till 1.1 billion. And if you go and look at the content, it would be all zeros here. And the same for here, where it would be all ones. So this is reality. and this is illusory or virtual. So virtual means illusory or fake, however you want to call it. We typically use the more noble term virtual, but keep in mind that this is what at the end of the day all that it means. It's not the real thing. This is the real thing. And so after this process P5 begets this dynamic memory, it's under the impression, it's under the illusion that this memory is contiguous. So therefore, it would treat these addresses as the actual addresses when in fact the address from 2 billion to 2.1 billion must get translated. So they must undergo indirection. Indirection means also translation. So the address must get translated from 2 billion. So 2 billion gets mapped to 1 billion, and 2.1 billion gets mapped to 1.1, and in this case 2.2 gets mapped to 3.1. So here, if in this code somewhere it performs a instruction that accesses this memory, and it wants to say access this address 2 billion. So this is not any particular assembly language, just some toy language. So it says move the content at address 2 billion, so it should be all zeros, to some register R3. So it could be EAX, EBX in our x86, but this is meant to be very generic, has nothing to do with x86 per se. This type of situation arises pretty much in all modern architectures. So when the code, when the actual instructions of process P5 has such an instruction that accesses main memory, because that's supposed to be the address of main memory, what actually happens? When this instruction is being decoded, so the CPU does fetch, decode, and execute, as we know. So when it's going to decode what this instruction means, it finds, oh, this first operand is a memory access, and it issues this address 2 billion, which is fake, it's virtual. So what is the true address, the true physical address of 2 billion? That's where the hardware support comes in. It consults a translation mechanism, so that's called address translation. And for speed, it does it with the help of hardware, because otherwise you would have to have code that performs this translation, which now you can imagine is going to make every memory access be slow. It would be quite excruciatingly slow, because you need to then translate this into this address, here in this example 1 billion, in software. That would of course make no sense if you want to have a reasonably fast running computing system. So with hardware support, this address translation needs to map this fake address 2 billion to its true counterpart in physical memory, 1 billion. And only after this goes through is the actual physical memory accessed with this address. Now, if the same process here, P5, accesses or executes another instruction down here, say move, and now the address of the first operand is, say, the last address here, let's call it 2.2 billion. Again, keep in mind, when we are counting from 2 billion, it has always got to be where you're going to subtract 1 from this, because we start at 0 onwards. So but we are not concerned about those minor details. So suppose this is the last address of this contiguous address of size 200 megabytes, and it wants to put the content, which is all ones, at this address into some register, say R5. That's the instruction. Again, the CPU at the decoding stage would then have to, at the end of the day, with hardware support, result in address translation where this address 2.2 billion, which is fake, which is virtual, must get translated to its actual physical address, which happens to be 3.1. And only these addresses, which are the two addresses, are seen when the actual physical memory is accessed. All of this happens before. So this is all prep. So this is all preparatory. So this is all a preparation, prep for the actual real deal. And through this address translation now, this content here is stored in this true location. This content of all ones is accessed at this true location, and these two regions of 100 megabytes are clearly not contiguous. They are fragmented, but as far as this process P5 is concerned, it's given the illusion that it is accessing a contiguous chunk of memory of size 200 megabytes. And when I talked about this address at the decoding stage being mapped to this address, which are the true physical addresses, it's just a logical interpretation. In reality, we can view this as being part of the execution because it's after the decoding is complete, and then this fake address is trying to reach the actual the actual memory unit, that there is another step, this intermediate step of address translation that intervenes, that implements this indirection operation so that this address is then translated to this address is then translated to its physical address before these addresses then are seen by the actual physical memory. So in that sense, it's more a part of this part. But those details, we are not starting architecture for its own sake, so those details don't matter. The key thing is, in between these fake addresses hitting the actual physical memory, a remap, this indirection is performed by this translation mechanism with hardware support that changes the address, and this is how we're able to allow this memory access, this memory get operation to go through and beget contiguous memory when in reality this memory is splintered. It is fragmented into disjoint areas, each of 100 megabytes big. So this is the idea of indirection, in particular using address translation, that addresses this problem of external fragmentation, where now if the total memory is greater or equal than the requested memory, that's the requested memory. So even though there's no contiguous memory that's big enough, if the total memory is big enough, then through indirection, that is through address translation, with hardware support for speed, we are able to give the illusion to processes that they get contiguous memory back. So the system call will succeed. It won't return an error. So we are not going to be satisfied with an arrow, it's going to get a pointer back. A pointer not in physical memory, a pointer in this fake virtual memory, and the process then can go on executing. It thinks its content of all zeros is being stored in this region of size 100 megabytes, when in fact, of course, this is just purely illusory. This content resides at this location in the actual true memory. Same for this region of 100 megabytes, all ones. Where do they actually reside? Not at address 2.1 to 2.2 billion, that is the addresses, but at address 3 billion till 3.1 billion. That's where the content actually is. So all of this stuff is fake. So let me use plain language. It's fakery. It doesn't exist. There is no such thing. We are just making it seem as if it exists. The only true thing is this thing. That's the only true, real physical thing. And this is what it looks like. This is how it looks like. It's still fragmented, it's still splintered, but we can give the illusion to this process that it's not through this technique. So that's the key idea behind using indirection to address this external fragmentation, which is a very serious problem. But now you can see from here that for every instruction whose operand or whose operands access memory, so they have a memory address being specified, all of this must happen. And clearly we cannot do this in software, because then you would have to write some software code with if, else, which then translates to tens of instructions that you then have to run to make sense of what the true address of this should be. So every such instruction which references memory would be slowed down by a factor of 10, 20, 30, 40, who knows. And that's of course not acceptable. So because this has to occur for every instruction that's going to access an address in memory, it has to be done for speed reasons with hardware support. This is not optional. And as you can imagine, this is quite expensive because you are now making a major commitment. You are building hardware so that you allow such a translation to intervene to get the true physical address before it hits the actual memory before it actually hits our main memory unit. So that's a major commitment. It of course is going to ramp up the cost of hardware quite a bit. So the question is this really justified? Yes, from the issue of external fragmentation, where if we don't address this, then because the memory gets splintered and you have apps that need contiguous memory, those system calls are likely then going to return an error. And if that's not acceptable, it's not acceptable. But the good thing is that at the same time of addressing this external fragmentation problem that we are using as a first motivating factor, doing this has other significant benefits. So that's what we're going to now mention. What other benefits does this have? So benefits of hardware support, which is very costly, which is quite involved, for indirection, that is address translation for every memory access, address translation. So one is what we started off with, external fragmentation. So hopefully this now is clear. But there are other benefits. Second very huge benefit that comes from this is what we call virtualization. Well, we just said that this is fake. So what is the true or benefit? To be more concrete, it facilitates, this allows a simple programming model. So this is a very high level concept, simple programming model. This is to say, when we have app programmers who are coding apps which then become processes, like this process 5. When we have coders of compilers, so GCC is just an app, it's a piece of software that then runs as a process and it does its job. We want to make sure that those who live in this world of building apps, which is of course the customer of an operating system, these are the guys whose job we are trying to make easier through the work of an operating system. It's a purely utilitarian viewpoint that at the end of the day, the bottom line purpose of an operating system is to allow applications to run efficiently and share a given computing system in terms of its resources. That's what it's there for. There's nothing more fancy than that at the basic utilitarian level. So when these humans who are programming apps, including these types of systems apps or more systems related apps, we still want these guys not to worry about physical memory limitations. Physical memory limitations. So the actual physical memory here that we discussed will become fragmented, it will become splintered like this one-dimensional Swiss cheese. And that's the reality, that's the true physical memory. We don't want programmers to deal with this actual reality. We want them to give the illusion that they live in a world where this is not the case. Instead, they ask for 200 megabytes of contiguous memory. We give it to them, if possible. They are under the illusion that it's contiguous. When this part is from here, this part is from here, this part is from here, all of that headache, all of this gap of reality versus illusion is filled in by the operating system. So the operating system, our kernel, is the guy that makes this happen. So these guys can live in this nice, clean world and get the illusion that this is contiguous. That's number one. But number two is, now that we are committed to investing in this hardware support, that for every memory access performs address translation, a major undertaking, but needed for speed, we can just go all the way. So using the same hardware support, we can go all the way and not limit the benefit just to external fragmentation, but we can now tell every process, hey, you process P5 or you process P7, you own the entire memory. So P5 thinks all of this memory is mine. P7 thinks all of this memory, all of this main memory is mine. Every process thinks they own the entire memory. Of course, there's only one shared memory, one common memory, this guy. That's the physical memory. That's reality. But by virtue of having this hardware support that we are now committed to, we can just go all the way and allow every process to think that they own the entire physical memory, when in fact they don't, but we provide the illusion. And that is called virtualizing memory. Virtualizing memory or virtual memory. We are giving this illusion. So now you can also tie this in with the illusion that we provided under process scheduling plus context switching. All the details aside, what did an OS accomplish at the end of the day at the high level? It virtualized the CPU. We made P5 think it owns the CPU. We made P7 thinks it owns the CPU. Here we are assuming just one CPU, but it's the same if we have 4 CPUs. We make them think that they own the CPU. Obviously, the CPU is not owned by any one process, because through scheduling and context switching, we continually context switch in, context switch out, context switch in, and context switch out the same CPU that's being shared. But whenever we do that, we then put the CPU, we then restore the CPU back into the state so that P5 can continue running. And if P5 is kicked off, then we save the state of the CPU so that when it is brought back in, we can then put it back into the state where P5 was before it was context switched out. Same for P7. So we are doing a lot of processing here, the overhead of context switching, to ensure that P5 thinks they own the CPU. Same for P7. So what we did under scheduling, context switching, under process management was, at the end of the day, we allowed the CPU to be virtualized. Every process thinks they have their own CPU, when the reality is it's being continually switched around from one process to another, and we make it so that they all live under this illusion. Same thing now for main memory. We now go all the way and we say, hey P5, the entire memory is yours. Hey P7, the entire memory is yours. When they ask for dynamic memory, for heat memory using getMem, then we give it back from this address space. We say, okay, this is your memory. But this memory here is here, here, here. It's splintered. But that bookkeeping is done by the operating system. The kernel handles all of this translation business with hardware support so that we can provide the illusion to P5 that it has this contiguous memory when in fact it doesn't. Same for P7. It thinks it has this contiguous memory, but it doesn't. But by going all the way, we are now providing a simple programming model, because the programmer, whether they program in C and then ask GCC to translate into machine code, or they program in assembly code, it's still a program at the end of the day. That programming world benefits from the illusion that the program works under the assumption of this entire memory belonging to this one program that's now running, hence became a process. So in our 32-bit x86 architecture, it would be from 0 byte till 4 gigabyte, 0 byte till 4 gigabyte. They each think they own the entire 4 gigabytes of main memory, P5, P7. If there's a P9, P101, all of these processes, they all think, oh, I own the entire 4 GB of main memory. And we make it work by using this address translation with hardware support and then mapping the addresses to actual locations in this shared physical memory. So this is all shared among everyone. Like the CPU was shared among all these processes, the memory is being shared. But they thought, oh, this belongs to me. Each of these guys thinks the entire memory belongs to it. So huge, huge benefit. Number 3. So what's the number 3 benefit? Let me use here black color. So I'm highlighting 3 aspects. There are more, but I'm highlighting the principal ones. External fragmentation, simple programming model that's made possible by going all the way and by virtualizing memory. And number 3 is what we would call memory hierarchy. And this is a separate issue from these 3, but it's made more easier by having 1 and 2 in place. That is, by having this hardware support for address translation that we commit to. This facilitates what we call memory hierarchy. So what is memory hierarchy? We are not going to be satisfied with this illusion alone, because this physical memory, this main memory, compared to CPUs, is slow. It is very slow. So we are going to go even further and provide an illusion that this memory is actually fast. It's close to the speed of the CPU, when in fact there's a large gap. So in reality, you don't want to actually go to your true memory to read write, because doing so is going to slow down your CPU, because it's got to wait until the data is read or written to the physical memory. So going to RAM is not a good idea if you can avoid it. So the third thing here is we are going to provide the illusion that this slow memory is actually fast. It is going to be much faster. And that's going to be done through a technique that you all know from computer architecture called caching. So to all of this, we are going to add caching, where address translation plays an integral part. But this is not the same as this. It's another dimension, but it can fit nicely in this framework with this hardware support, which then gives us the illusion. But it's reality, because it's going to speed things up. It's going to make things faster. So for these 3 main benefits, it makes sense. We can justify having hardware support, which is costly, that allows address translation to be done per instruction that accesses memory. And through hardware support, this can be done quickly. And the benefits are this guy, simple programming model, and it facilitates this memory hierarchy that then adds to this illusion, which becomes reality, because it does become much faster through a technique called caching. But it's called multi-level caching, because we are not going to have just one cache, we are going to have multiple layers of caches. So these are all the good things. But what are the bad things? Because in systems, in reality, there's no free lunch. If you gain something from here, you have to lose something elsewhere. and it's only by a judgment call that what you gain you view as being more important than what you lose, that you then decide to make this work. So one drawback of this guy was obviously cost, the hardware cost. But there are other equally important tangible costs that we must keep in mind. So let's see what they are. So cost, that is overhead, so we use the term overhead now in systems, of using this address translation, this virtualization that has the benefits 1, 2, 3. So these are all the benefits. And now we're going to pay attention to overhead. The overhead is every process, P1, P2, P3, let's say P300, they all think that there's this in our x86 32-bit architecture. Just to make it concrete, they all own the same physical memory, and by default from 0 till 4 gig. 4 gig, 0 bytes to 4 gig. Obviously, to make this true, to make this actually true, since there are here 300 processes, we would need 300 times 4 gigabytes of memory to make this actually physically true. But this is too much. We don't want that. We have only 4 gigabytes and we still want to make sure that each of them lives under the illusion that they own the entire 4 gig of physical memory. But to make that work, we have to now pay an overhead cost. And this overhead cost is the address translation that's done by P1. So let's give an example. Here is the true physical memory. So these are all illusory. So this is all virtual, fake. And this is now physical. This is the only true thing, physical memory. And it's from 0 till 4 gig. Suppose we have installed 4 gigabytes. If you have 8 gig, you have 16 gigs, or you have 32 gigs on modern computer, the same thing here applies. So this is the true physical memory. And suppose P1 performs get mem. I'm using again Xeno as an example. It says 100 megabytes. P2 also calls get mem, so the system calls get mem and asks for 100 megabytes. So both of them call get mem. And get mem, the system call, the kernel returns, suppose the same address as the pointer. Suppose the same address, 2 gigabytes. This is the address. So when P1 makes this getMem call, it returns the address 2 gig. When P2 makes the same call for the same amount of memory, this guy returns the same virtual address, fake address. So this guy, P1 thinks, oh, I own a contiguous chunk of 100 megabytes starting at 2 gig until, of course, 2.1 gig. But P2 thinks the same. It gets back the same starting address 2 gig and it ends, or it's of size 100 megabytes. But this is no problem because the OS, because this is the purely virtual world, so this is the fake world, is not where things are really happening. It's here where things are really happening. And so this area, let me call it A, and let's call this area B. And suppose P1, after it gets this region, puts all zeros here. So it puts into the actual content all zeros. And suppose P2 puts here all ones. That's the content. These are the addresses. that's the content of the map. And they think that they own this address, the actual memory starting at 2 gig until 2.1 gig, but of course both of them cannot. For A, this region, the OS, so this is the manager in between, maps A, suppose here, this is where A lives. So this is P1's region, and down here somewhere is where B lives. This is P2's memory region, both of 100 megabytes. And since they are disjoint, this here is filled with all ones, the content, and this is filled with all zeros, and there's no issue. The fact that both of them think that they own this area starting at 2 gigabyte as the address, that's referred to also generically as aliasing. That is, they're using the same address, but this address are mapped differently. This guy, if it's P1, gets mapped to this address range, and if it happens to be P2, it gets mapped to this address range. So that's all and well, but how is this actually done? Under the setup of one CPU being shared by P1 and P2, so they are now sharing the same CPU, which means we are now virtualizing the CPU. We are doing process management that we discussed earlier. And suppose P1 becomes current. So P1 is current. When P1 becomes current, we need to use P1's address translation mechanism to perform this mapping. Because for P1, this address starting at 2 gig until 2.1 gig gets mapped to this address. Suppose this is 3 gig and 3.1 gig. But suppose now P1 is context switched out and P2 becomes current. This is the new current guy. We cannot use P1's address translation because then when P2 wants to access its content, which is all ones, it would get here, which is all zeros. That would of course be wrong. So when P2 becomes current, we need to use P2's address translation mechanism. And under P2's address translation mechanism, the same virtual address 2 gigabytes is not mapped to 3 gig. Suppose it's mapped to here, and suppose this address is 1 gigabyte, and of course this is 1.1 gigabyte. So that when P2 is the current process and P2 aims to or tries to access its virtual address 2 gigabyte, the 2 gigabyte now does not get translated to 3 gigabytes as with P1's virtual address translation. It gets translated to 1 gigabyte. So they are at different places. So the aliasing issue is solved, but it's only solved because the address translation mechanism that translates, so this mechanism, it translates, it maps virtual address to physical address. That is what this guy does. And this mechanism that performs this translation has to change when we context switch. Obviously, because otherwise we would not be able to provide illusion number 2, virtualization. every process thinks they own the entire memory. Hence, we have aliasing happening. But how do we solve aliasing? We allow every process to have its own. So each process has its own address translation mechanism. And when we translate addresses, what do we mean by that? It can be viewed as a table, as a two-column table. This is a logical view, not the actual physical view, where in this column is the virtual address, and in this column is the physical address. So if, for example, we are now running P2 and we are now using P2's table, P2's table would say, oh, if I'm going to address this virtual address 2 gig, what is its true physical address? In this example, it's 1 gig. So this translation mechanism in computer science can be represented, it's not the only way, but can be represented as a table, can be viewed as a table. So hence we talk about address translation table, a two-column table. The first column is the virtual address, and the second column specifies its counterpart, which is the physical address. That would have this entry in it: 2 gigabyte of virtual address for P2's address translation table maps to 1 megabyte of physical address. But now, let me show this in green. P2 is context switched out and P1 is context switched in. So P1 is the current process. We cannot use P2 tables anymore because it would give us the wrong mapping. 2 gigabyte of P1's address should be up here, not down here. So when we context switch in P1, we need to bring in P1's table. So what does P1's table look like? So here is P1's address translation table. I'll just note it by table. It's a two-column table, same thing. And this is P1's table. This was P2's tables. And now we are switching the tables. And here, the same virtual address, 2 gigabyte, gets mapped to this location, which is 3 gigabytes, 3 gig. So before, under P2's table, it gets mapped to 1 gig. Under P1's table, it gets mapped to a different physical address, which is 3 gig. And hence, as long as during context switching, we switch the tables, so context switching now becomes more involved. It's not just a matter of saving a few registers and then we are done. We now need to switch the address translation table from that belonging to P2 to that belonging to P1. So there's this switcheroo that we have to perform. And when we do so, everything works fine. So this means these address translation tables, they are all per process tables. So every process has such an address translation table. This is P1's. This is P2's per process. So if you have 100 processes, P1, P2, P3, or here we have 300. Every one of these guys has their own per process table. So prior, every process needed to have its own stack. So there was a per process private stack. So we know that from process management. That was minimally needed to make the notion of a thread of execution, a chain of instructions that we execute, a thread. That's the meaning of thread, a process. It needed at least a stack to make it work. All the rest can potentially be shared. The code, data, everything can be shared, but it needs a per process stack because in modern software, we build software using function calls, and therefore we need a stack to manage all this caller-callee business that we talked about. But now we have another per process essential data structure, which is we need a per process address translation table. And in our context switch routine, in the case of Xenu, but this is the same for Windows, Linux, everywhere, all of these are common. I'm just using Xenu as a concrete example because you know the details since you did it in the lab, so you coded all the details. But in context switch, we needed to switch the stacks from the old guy to the new guy. So we did that already. But here we need to switch the address translation table from the old guy to the new guy. And that too is a major undertaking, and the cost, the overhead of doing all of that will become more apparent when we talk about memory hierarchy, number 3. So that's why they are all interrelated, and only after we reach 3 can we see the full picture of what all of this does for us. So this memory virtualization is a very costly affair. It needs all this hardware support to make it work. But once we have it, we see all of its benefits. We are keenly aware of all the costs, the overhead especially, that come into play. Here I'm pointing out that context switching, that perhaps we might think we are done with. It's not done. The context switching that we did earlier on was the basic of basic context switching. Now, as we add more things to the kernel, in this particular case, we are trying to make virtual memory work. We find that context switch has to now be enhanced by switching the per process address translation table, which is essential to making all of this work. One last point, and then we will stop here, is how big is this address translation table? So, size of per process address translation table. What is the size? Well, let's be concrete, and then it can be easily generalized. We are using x86 32-bit architecture, so from 0 byte, from 0 byte till 4 gigabyte. So suppose a process P1 is memory hungry and it needs all of this 4 gig. Same for P2, same for P300. These are our 300 processors. They all think that they own this thing. Well, they have to be able to translate each and every one of these addresses. So they would have to translate each and every one of these addresses, which is virtual, to a potentially different address, which is the true physical address. So in the worst case, the table that performs address translation, so this is to translate addresses, this guy, address translation table. This guy must have, in this instance, ballpark speaking, 4 billion rows. This table. That of course makes no sense. This means for this kernel data structure alone, the table is huge. So that of course won't do. So what you can do is you can cosify this memory and say we're not going to view memory in terms of bytes for our purposes. Yes, at the end we are going to deal with bytes, but we're going to add another layer of abstraction, this too with hardware support, where our minimum unit is going to be a block of bytes. In Xenu, when we did get mem, etc., we committed to in Xenu to use a block size, which is a fixed block size of 8 bytes. So even though we request 6 bytes, we get back 8 bytes. And that was called, the waste was 2 bytes. And we called that internal fragmentation, which we said was not a big deal. Here we are going to create larger blocks. A very popular block size is 4 kilobytes. So this is of course in the power of 2, but roughly 4,000 bytes. So you ask for 20 bytes, you get back 4,000 bytes in powers of 2. So it would be 4096 bytes to be more exact, but we don't care about these details at this conceptual level here. When you do calculations, of course, you have to put all of the details in, but at this juncture. So here, the internal fragmentation is bigger because you are only needing 20 bytes, but you're getting 4 kilobytes back. But still, it's not considered to be a big deal. It's not purely minor, but still the key issue is always external fragmentation. This we can basically live with, the fact that we are still wasting much of this memory because this guy only needs 20 bytes, but by having a minimum size of 4 kilobytes, the bookkeeping is made much more efficient. So the table size would have to be, in this case, 4 billion rows. That's too much. But if our unit is fixed size of 4 kilobytes, here as an example, then everything is tallied in units of 4 kilobytes. So how big is our table then? Our table then is, this is 4 gigabytes of memory, but we are now accessing memory in units of 4 kilobytes, nothing smaller. So 4 gigabytes, which is 4 billion bytes, divided by 4,000 bytes, that gives us 1 million entries. Much smaller than 4 billion entries, rows entries in the table. So this table has shrunk obviously by a factor of 4,000. So it's much smaller, so it's much more doable. But still, if you have 300 processes or you are a server with thousands of processes, per process having a table, a per process translation table of this size is still large because you have to multiply it by 300 for this, or if you have 3,000 processes by this. So this is not minor either. So we need to shrink this size even further, compress it. And we will talk about how to do that. But here I'm highlighting the overhead issues that we have to be cognizant of and that we have to carefully manage so that we get the significant benefits of implementing this indirection operation through address translation, and we get 1, 2, and we will discuss 3 next, without paying a huge overhead that would perhaps defeat all the benefits that we get from here. So we have to be keenly aware of the overhead issues that arise, how to manage them so that we can reap most of the benefits of 1 to 3 without paying a huge penalty in terms of overhead. So let's stop here.